Hello and welcome to this Vortex Studio video tutorial where you're going to be learning how to create a mechanism. In this video, we're going to be creating a simple drivable forklift from a graphics gallery. In order to complete this tutorial, you're going to need Vortex Studio installed as well as the demo scenes package. First, from the new document section of the main menu, click on New Mechanism. In the Explorer, let's rename with the F2 key, let's rename our mechanism forklift. And by using Ctrl S, let's save our mechanism in our working folder. Next, we're going to be adding the forklift graphics gallery. So from the graphics section of the toolbox, let's insert galleries from file. From the window popping up, click on Browse and look for the demo scenes folder. We're going to look for equipment, forklift, graphics, forklift.graphics gallery. Now, we could simply select this graphics gallery, but the problem is our mechanism is going to point to a gallery that is not in the same folder as where it's saved. So let's copy this gallery, copy, and let's paste it in our working folder. Okay, so now my graphics gallery is saved at the same level of my mechanism. So even if I move the mechanism folder, it will still work. You won't have any issue of the mechanism not finding the gallery file. Now from the Explorer, we can expand the graphics gallery and look at the different nodes that we're going to be using in order to create our parts, right? In this first section, we're going to be creating parts for the body as well as the wheels of this forklift. So here, let's right click on the body node and click on Create Part In, which will create an assembly for us as well as a part in this assembly. Let's also do this for the front left wheel. So right click on it, create part in our existing assembly. Same thing here for the right wheel, create part in assembly. And we're going to also create the part for the rear wheels and the rear wheel caster, which will be the pivot allowing us to steer those wheels. You'll notice that this creates a connection container called skin. So this is where the dynamic parts are connected to their graphic node's counterpart. All right. We can already test this by playing the simulation, and we'll see that the parts have mass, and we can also see that the graphics is following those parts. So next we'll define collision geometries for these parts. So let's right click on the front left wheel and create a best fit geometry, and we'll choose the cylinder because the cylinder fits the shape of the wheel pretty well. Let's do the same thing for the front right wheel. So best fit geometry cylinder, as well as the rear wheels. Best fit geometry, cylinder. We already see the debug view of our collision geometry. If you don't see it, you can always press Shift G in order to activate or deactivate the geometry view. Let's also generate a collision geometry for our body part here. So create best fit geometry. And instead of choosing a cylinder, we're going to be choosing a convex mesh decomposition, since obviously our part is much more complex than our wheels. On this new window, for level of detail, we'll keep it at intermediate. You can always choose custom and define the advanced parameters, but here we'll just keep it as intermediate. Next, save the mechanism using Control S. Keep in mind that this will also save the assembly file at the same location where your mechanism is saved. So now we can double click on the assembly from the Explorer in order to open it in another tab. Here we will be able to define the part's mass and inertia, as well as defining constraints between different parts. So let's expand the assembly in the Explorer and select the body part. In this properties window, in the parameters tab, we can change the mass to 3000 kilograms, so 3 tons. And we can click on the compute inertia and com here. So what this does, it uses the collision geometry in order to evaluate the distribution of the mass. You can actually visualize this inertia tensor by right-clicking on the eye icon of the part in the Explorer and selecting inertia as well as center of mass. It's easier to visualize if you deactivate the collision geometry view. The other thing you can do is by selecting this part, you can also use the resize inertia tools here, and you can manually modify the shape of this inertia in order to perhaps fine tune it. So let's do the same thing for the other parts. So for the front left and right wheels, we'll change the mass to 30 kilograms, and we'll also compute the inertia income. Same thing for the right wheel, 30 kilograms. And the back wheels will be double the mass, so 60 kilograms, and compute the inertia. We won't be touching the rear caster here because its mass will be pretty much negligible. So keeping it at 1 kilogram with a very small inertia will be good enough. So the next step will be to define a hinge constraint between our front left wheel and our body. So the best way to create a constraint between two parts is to select the first part in the constraint, click Control, and select the second part. So from the toolbox, go to Common Constraints and double click on the hinge. So this creates a constraint that's located on the reference point of the first object that you selected. Okay. If we click on the actual constraint in the Explorer and we look at its properties, we'll see that the part 1 was defined as the front left wheel and the part 2 was defined as the body. If we had selected them in the reverse order, it would have been the opposite, the body being the part 1, but the front left wheel being the part 2. The other reason why we selected the wheel first is because by selecting an object first, it also defines the default value for the reference object of both parts. To give you an example, if the reference object for the part 2 was also body, it wouldn't work right away because one part of the constraint uses the reference of the body and one part of the constraint uses the reference of the wheel. So they have an offset when the simulation is starting, right? And obviously this offset is unwanted here because if we test the simulation, everything explodes. We can take a look at the step-by-step sim here. We can see that both parts try to, clamp to the same location, and it makes everything go swoosh. Okay, so let's fix that by putting the front left wheel to be the reference of both parts. Now we see that it makes a bit more sense. The other thing that we need to fix here is the primary axis for both of these references. So the hinge, which only has 1 degree of freedom, uses the primary axis to define its rotation axis, right? So right now we can see that the primary axis in red or in purple is defined as the x-axis, which is not good because obviously we want the wheel to be turning around the y-axis here. So we can simply press this button here to change the reference to be the y plus axis. And the secondary axis, we can simply put it back to the x plus axis. Yep. We can do the same thing for the second part, or we can simply click on the attachment position window and copy offset from the first part. So if we click apply here, both references agree on the same rotation axis. So we can test this again, and we'll quickly see that there's a problem here. Our wheel is not quite, turning as we would expect. This is because we don't have any collision rules. Actually, if we press Shift C, which activates the contact view, we see that there's a lot of contacts between the front wheel and the body, right? If we activate the geometry view, it's obvious why. The wheel is kind of starting inside of the collision geometry of our main body. So the way we'll prevent that is by simply adding a collision rule inside of our assembly. Right? Collision rules can be found in the basic section of the toolbox. So let's add one. And in the properties of the collision rule, let's add a rule. So this rule defines if there is or not collision between two objects or two parent objects. In our case here, we simply don't want any collision anywhere in our assembly. So we can simply drag and drop the assembly in both fields of this collision rule. course, we don't want to activate the collide option here because we don't want those objects to collide between each other. Yep. So if we try this again, we can use the Alt key here to kind of pull on our main body here, and we can see that our wheel is actually, rotating freely around its axis. So let's repeat this process for the second wheel here. So the front right wheel, select it first, press the Control key, select body, and then from the common constraints, let's add a hinge. Same thing again, primary axis has to be a y plus and secondary x plus, and copy the offset for the second part. We'll repeat the same process for our caster, right? So we want our caster to rotate around the z-axis here, right? So we want to create a hinge between the caster and our body. So select caster, Control key, body, hinge, and then the primary axis should be the z plus. We can keep the y-axis as the secondary axis here. Again, copy the offset for the second part, and we'll have a caster rotating around the z-axis. We also want to create a hinge constraint between our back wheels and our caster. So let's repeat the process. Rear wheel, Control key, and then caster. Of course, we select the wheels first here because they have a better reference to define the rotation axis. So primary axis should be y again. So y plus, x plus as the secondary. Click on this button, apply, to copy the offset. And so now we've created 3 hinges. Of course, we'll need to motorize or lock some of those constraints in order to have, a functioning mechanism here. But we can see that at least the core concept of our forklift is working. A good way to be organized here is to create folders from the basics. So we'll create a parts folder, put all of the parts in this new folder. We'll add another folder and name it constraints to add all of the constraints in this new folder. Before we continue to the next step, I forgot to assign materials to my parts. So let's do that now. Let's expand our parts folder, and we're going to be selecting all of the collision geometries that we created for our parts. In the case of the body, we've created a convex mesh decomposition. So this created a lot of convex mesh. So let's select them all. And we'll change their material to chassis. Could also do a small adjustment here. We see that some collision geometries was created for for a light texture. We can of course delete those by simply selecting them and deleting those extra geometries. Let's select our wheels geometry. Now we can use the Control key to select all of them. And the material here, we'll use wheel. Next thing we're going to do is to define some motorized and locked behavior for some of our constraints. So here, our steering constraint, right, which is the constraint between the caster and the body, we'll want it to be locked, right, so we can set a certain angle of steering. And we'll want our back wheels to be motorized, so we'll be able to set up a certain speed and a certain torque to our back wheels. So let's select the hinge constraint between our caster and our body, and we'll go to the Inputs and Control Axis tab. Here we'll see that there's only one section, which is the only angular component of our constraint. So instead of having a free control, we'll set a locked control, which will open this lock section. We won't change anything else here, but if we start the simulation, we'll see that our constraint is not moving like earlier, and we can actually set up a certain degree or a certain angle for steering. Let's put that back to 0. And we'll also set up limits because we don't want the wheel to go farther than minus or plus 90 degrees. So let's activate limits. And we'll set a lower limit of minus 90 degree and plus 90 degrees. So if we try again, this will make it so that even if a desired position is set up to be, for instance, 150 degree, the wheel will not turn more than the limit we set up, which is 90 degrees. Now we'll motorize the constraint between our back wheel and our caster. So let's select that constraint. And again, in control axis, we'll change the control to be motorized instead of free. So of course, this will activate the motor section, where we will see that we can actually set up a desired velocity for our wheel. So let's try, for instance, 300 degrees per second. We'll see that the wheel now has a certain velocity, which match the desired input. For this constraint, we won't be setting up any speed limits, but instead we're only going to allow the constraint to use a certain maximum and minimum torque. So we'll only allow here 1500, or rather minus 1500 as a minimum force and plus 1500 as a maximum force. So here, even if we set up a desired velocity of 6 million degrees per second, well, our mechanism is not going to be exploding because it has access to infinite force. Now that our constraints for the driving of our forklift are defined, the next step will be to add control logic. So to do that, we'll have to go back to the mechanism. So let's save our assembly and close it. And back in the mechanism, let's create a folder called forklift controls. In this folder, we'll add a joystick. So let's search for joystick in the toolbox. This component will connect to any X input or direct input gamepad, just like an Xbox controller or any other controller. We'll also add a connection container from the toolbox again. Let's rename it forklift controls connections. So from the joystick controller, we'll find the vertical axis of our left joystick, which is axis Y, and we'll drag and drop this property into our connection container. Let's do the same with the horizontal axis of our right joystick, which is axis Y rotation. So these two outputs will correspond to the throttle of our forklift as well as the direction. The next step will be to connect these outputs to the desired position and velocity of the constraint that we defined previously. So let's go and find these constraints. So in our assembly, in our constraints folder, we have the constraint between the back wheels and the caster. And we'll want to control the desired velocity of this constraint. So let's drag and drop this input. Do the same thing with the caster constraint, which will be our direction. In that case, it's a locked constraint, so we'll change the desired position for this constraint. So let's connect the two. So the throttle being the desired velocity of our back wheels, and the direction being the desired position of the caster related to the body. So we can already test this by going back to the 3D view tab and by starting the simulation. So here my left joystick is controlling the speed of the forklift, and my right joystick is also controlling the direction of the back wheels. Now, of course, you're going to notice that our forklift is going extremely slow right now, and the direction is not, being controlled properly. We would want the back wheels of our forklift going from minus 90 degree to plus 90 degree, right? And of course, we would want our forklift to perhaps go a little faster than this. So coming back to our connections, the reason why it's going so slow and we can't really control the position is because the range of our joystick outputs only varies between -1 and +1. We can see that by playing around with the controller and looking at the output data. It's only going from -1 to +1. This data, both the desired velocity and the position are in radian, and so -1 and +1 radian is about 57 degrees. So our velocity is only going at 57 degrees per second, and our position only varies between minus and plus 57 degrees. So to make up for this issue, we'll create a script that takes in the outputs of the joystick and increase them in order to get the desired values that we want for both our speed and the steering of our forklift. So from the toolbox, let's search for script. We'll choose dynamic script here because it uses the new Python 3 interpreter. So let's add that to our folder also and rename it forklift controller. Next, we'll right click on this extension and click edit, and then we'll add the inputs and outputs that we need here. So let's add two inputs. They're both going to be of type double. and we'll name them throttle and steering. This will produce two outputs, also of type double, that will name velocity. This will be the velocity of our back wheels, and position, which will be the position of our caster constraint. In the properties of the script extension, in its parameters, it's expecting a path to a script file. So in the folder of our mechanism, what we'll do is we'll create a Python script file. So let's rename it forklift controller dot Python, and we'll edit this empty script. You can use any text editor. All right, so let's write our script. We'll first import the Vortex library. So you can simply do import Vortex. Next, we'll define a function that is called at each step of the simulation. Right? So let's write def pre_step. It's expecting extension, which is the extension object of our script extension. So here we'll store our inputs from the extension. So we'll do extension dot inputs, and we remember we had our throttle dot value. We'll store this in variable we'll call throttle. Let's do the same thing for the steering. So we'll do steering equals to extension dot inputs dot steering dot value. Now, what we'll want to do next, we'll want to multiply these values by a certain factor and send them to our outputs, right? So we have extension dot outputs dot velocity will be equal to throttle time, well, certain factor that we'll define later. Okay. Let's do the same thing for our position output. So extension dot outputs dot position equals to steering times, well, another factor that we'll define. A little mistake here. It's velocity dot value. This is very important because this is the value component of the velocity output. Now we can start by simply trying to multiply this by some number, some random number. So let's multiply this by 6, and the steering, let's multiply it by something like 1.5. Oh, mistake here. Steering. Save this, and back in Vortex, we'll set the script path to the script that we just created. So we can test this. In order to see any errors or anything from the script, you can always open the Python output window from the view tab here. I see I already have an error, so I'm getting an error in line 8. Position does not exist, so let's see. Right, so I forgot to capitalize position name here. Let's try that again. We can always clear the output, so we can see that our script doesn't have any more errors. The next step, of course, is to add our script inputs and outputs to our connections here. So we'll do that. So we'll delete the connections that are already there using the delete button. And we'll add all the inputs and outputs of our script into our connections container. So here our axis Y will be connected to our throttle input, and axis Y rod to our steering, and the velocity to the desired velocity, position to the desired position of our caster constraint. So let's try that again. So I see that now when I move at my joystick, it's outputting -1 to +1, but in reality, the output of the script is from -6 to +6 because, of course, we multiplied it by a factor of 6. Forklift is going a little faster, which seems pretty good. And our steering seems to be quite fine, actually, because 57 degrees multiplied by 1.5 is about 85.5. So we're almost at 90, which seems already pretty good. Although our speed of our forklift could go a little faster, in my opinion, so we could try to modify the script in order to increase this parameter. Now, if we modify and save the script, we need to restart the simulation in order for changes to take effect. So now we see that our forklift is going much faster to a speed that's pretty much acceptable. The other thing that we could do is instead of hard coding these parameters, we could also add parameters to our script. So let's do that. Right click on the forklift controller again, click edit, and on the bottom here we can add parameters. So we can call this speed factor of type double and steering factor type double again. Back in our script, instead of multiplying this by 10, we can simply multiply this by the extension dot parameters dot speed factor dot value. Extension dot parameters dot position position. No, it was steering factor dot value. Save this. Try it again. So now, of course, it's multiplying by 0. Nice thing about this is I can actually change those values manually. And test them as I go. So here, 20 is perhaps a little bit too fast. Our forklift is getting way too unstable. So 15 looks like it makes sense. And of course, this value, if we want to be precise, would be 90 divided by 57, which would be 1.57. Now we can see that forklift is allowed to turn almost around itself. Let's save our mechanism. Last thing we're going to do in this video is add a camera to our forklift. So from the toolbox, you can search for camera, and we're going to use a perspective camera. Using the move tool, you can move it to be positioned somewhere close to the driver. You can also right click on it and activate camera to possess the camera, and you can actually move it yourself using the middle key as well as WASD to get a view that seems like it makes sense, right, for the perspective of a driver. Okay. If you want to get out of this camera, you can always press P. P gets you back to the perspective viewport, right, the default perspective viewport. Okay. Now, if we test this and we possess our camera and we begin driving our forklift, you'll notice that the camera is not following the forklift. So in order to make the camera follow it, what we'll do is we'll use the skin connection container that was created for us earlier. Let's double click on it. Okay. And by clicking on the camera, we'll insert its parent transform. And we'll connect it to the part that we want to follow. So it wouldn't make sense to follow any of the wheels or the caster, but it would make sense to follow the body. So let's simply connect it to the world transform or output transform of the body part. So now if we try this again, we'll see that our camera is following our forklift. So that's it for this video. Now, if you want to go further, you can use what you've learned here in order to complete the mechanism with the mast and the forklift blades. For this, you'll need to use a new type of constraint, which is the prismatic constraint. to get the linear movement between the blade and the mast. You can always refer to the textual version of this tutorial, which gives you the steps in order to complete the scenario.